Your retriever finds the right sentence, but the model still misses the answer because the surrounding section never arrives. I'll build small to big RAG in Python with Qdrant, so retrieval stays precise without losing context. This is the workflow you'll know how to run when we're done, which retrieves child chunks and then reads parent sections to answer. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Think about a long document like a manual or a policy. A dense paragraph holds the exact answer, but that sentence sits inside a larger section that gives the necessary framing. A plain retriever that returns isolated chunks can point to the sentence, but the reader model still gets confused without the parent section. Small to big RAG solves that by first finding small, precise chunks, then expanding into their parent sections to assemble a coherent context before answering. The idea is simple. We split text into tight child chunks that capture precise facts. We also keep parent sections that hold the broader explanation. At query time, we search the children for exact hits, then fetch the parents of the winning children and read those sections in ranked order. This keeps retrieval precise and contextually rich. It trades a little indexing work for much better answers. Now we'll set up the collections in Qdrant. This snippet connects to a local Qdrant instance and creates two vector collections for the small to big RAG flow. It imports QdrantClient and model helpers, then defines a shared vector size so both children and parents are schema compatible. The variable QC holds the connected client, which is reused later. The calls recreate collection, build RAG children, and RAG parents with cosine distance, so similarity scoring is intuitive. Keeping a dedicated collection per level avoids accidental cross-level search, while still allowing lookups by metadata. If you change dim, all vectors you write must match it. The printed list confirms both collections are ready to accept points. Next, we add a few child chunks and attach parent links. This example writes a few child chunks into Qdrant and tags each with its parent identifier. The list children contains compact tuples for chunk ID, parent ID, and text. The function embed creates a small deterministic vector per text using hashlib SHA-256, so results remain stable across runs. The qc.upsert call sends points to the RAG children collection using point struct with a vector and a payload that includes level, parent ID, and chunk ID for later joins. Payload fields are crucial because we will expand from hit chunks back to parent sections. If you add more chunks here, search later becomes more selective. The print confirms how many child chunks are indexed. Now we will run a query to find the best child chunks for a user question. This code issues a vector search against RAG children in Qdrant to find the most relevant child chunks. The variable query holds a short user question, and embed converts it into the same vector space as the stored chunks. The function qc.search returns scored results, where higher scores indicate better matches under distance cosine. The variable hits collects the top two candidates so we can both inspect and reuse them in the next step. Extracting top makes it easy to display which chunk won and how strong the match is. If you increase limit, you'll retrieve more candidates, but also risk diluting precision. The print shows the winning child and its similarity score. Next, we insert parent sections and pull only those linked to the child hits. This example inserts parent sections into Qdrant and expands child hits to their parents using a metadata filter. The list parents defines concise section texts keyed by parent IDs. The qc.upsert call writes them into RAG parents with 0 vectors since we will retrieve them by payload, not search by vector. The setPIDs gathers unique parent IDs from the earlier child hits. A filter with field condition and match any selects parents whose parent ID matches those IDs. The QC.scroll call then retrieves the matching parent points efficiently. If you add more candidate parents, the filter narrows results to only those late to hits. The print confirms how many parents were expanded. Now we rank parents and build a compact reading context within a size budget. This snippet assembles a concise reading context by ranking parents with the best child hit scores and enforcing a size budget. The dictionary scores tracks the maximum hit score per parent, so sections with stronger evidence are preferred. The variable pmap maps each parent ID to its stored text from parents' PTS. The list order sorts parents by descending score. Then a simple loop packs as many parent texts as possible into the character budget. Raising budget includes more context and may improve recall. Lowering it tightens focus and reduces token costs. The final context is ready for your reader model. The print shows the context size and the top-ranked parent. This toy example maps directly to a help center or a legal corpus. Child chunks are short answers or clauses. Parents are full articles or sections. The same pattern scales to larger corpora by batching upserts and increasing the ANN resources in Qdrant, while the logic for expanding child hits to parents stays the same. Recap. Small to big, RAG first finds precise child chunks, then fetches their parent sections for context. Use it when short hits need surrounding explanation, like manuals, policies, or dense knowledge bases. Caveat. It requires extra metadata and storage for parent links, and adds a small retrieval step, so budget your index and request costs. Wrap punch. Next step, tune the character budget that packs parents into the reader context to balance recall and token costs. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.